So in the previous section, we learned that we can add two linear models to obtain a third model. As a matter of fact, we did even more. We can take a linear combination of two models, so the first model times a constant plus the second model times a constant plus a bias, and that gives us a nonlinear model. And that looks a lot like perceptrons, where we can take a value times a constant plus another value times a constant plus a bias and get a new value. And that's no coincidence. That's actually the building block of neural networks. So let's look at an example. Let's say we have this linear model where the linear equation is 5x1 minus 2x2 plus 8. That's represented by this perceptron. And we have another linear model with equation 7x1 minus 3x2 minus 1, which is represented by this perceptron over here. Let's draw them nicely in here. And let's use another perceptron to combine these two models using the linear equation 7 times the first model plus 5 times the second model minus 6. And now the magic happens when we join these together and we get a neural network. We clean it up a bit and we obtain this. All the weights are there. The weights on the left tell us what equations the linear models have. And the weights on the right tell us what the linear combination is of the two models to obtain the curved nonlinear model in the right. So whenever you see a neural network like the one on the left, think of what could be the nonlinear boundary defined by the neural network. Now note that this was drawn using the notation that puts the bias inside the node. This can also be drawn using the notation that keeps the bias as a separate node. Here what we do is, in every layer we have a bias unit coming from a node with a 1 on it. So for example, the minus 8 on the top node becomes an edge labeled minus 8 coming from the bias node. We can see that this neural network uses the sigmoid activation function on the perceptrons.